Let's look at factoring quadratics when the leading coefficient, or a, is not equal to 1. Now here's the problem. The method we learned of finding two numbers that multiply to be equal c and when they're added together equal b, that method only works when a is equal to 1. It does not work if a is 1/2, 5, -11, or anything other than 1. So how do we handle the case where a is not equal to 1? Well, let's look at an example. We have a quadratic here, 15x squared plus 95x minus 70. How do we factor that? Well, I'm going to walk you through a step-by-step process. When I tell you to, stop and take notes. Step 1. We factor out the greatest common factor from all three terms. Now, in this case, the greatest common factor is the number 5. It divides evenly into 15, 95, and -70. So we're going to factor out 5. We must always start with the step. There isn't always a greatest common factor. Sometimes we don't need to do this. But if there is one, this process will not work if you miss this first step. So we end up with 5 times 3x squared plus 19x minus 14. The next step is to multiply the value a times the value c. So a is 3 and c is 14 now, so let's multiply 3 times -14 and we end up with -42. The third step is to rewrite this expression, our quadratic expression, inside the parentheses without the a and with the ac. Now let me show you exactly what I mean here. This is just a temporary form of our quadratic expression. We're going to eliminate the 3 and we're going to replace a with a times c, as we did here in this expression. Now, stop now and copy down everything on this slide, taking care that especially you get the example. Step 4, we're going to factor our temporary quadratic. Now our temporary quadratic ended up being x squared plus 19x minus 42. We're going to factor that by finding two numbers that multiply to be -42 and add to be plus 19. And it happens they are -2 and plus 21. So we're still working here with our temporary expression. Step 5. We're going to divide both of these numeric values that we found by the value a. Now our a was 3 after we factored out the 5. So we're going to divide 2 by 3 and 21 by 3. You can probably guess that step 6 is to simplify these expressions. Now, as you can see, 2 cannot be divided evenly by 3, so that is in its most simplified form. However, 21 divided by 3 is 7. So we simplify these numeric expressions. Last, and probably most important, any one of the numeric expressions that cannot be simplified, in other words, it remains a fraction, we're going to take the denominator and kick it in front of the variable in the parentheses. So I'm going to take this 3 and move it in front of the x. And at that point, I'm done factoring. I don't have anything else to do here because this one is completely simplified. So my final answer is 5 times 3x minus 2 times x plus 7. If I multiplied these two binomials together and then multiplied that whole thing by 5, I would end up with my original quadratic or trinomial that I began with. Stop now and copy down the rest of these steps, taking care to include the example. All right, let's take a look at some examples. That's really the best way to walk through this process. So we start with this quadratic, negative 6x squared plus 15x plus 36. Now our first step was to factor out any common factors. In this case, negative 3 is a common factor, so I'm going to factor that out before I start. That is step 1. Next, I'm going to multiply A times C. So that's 2 times negative 12. That gives me negative 24. And I am going to eliminate the value of A, or 2, and replace C with A times C. Now this is just a temporary expression here as a part of my process. Then I'm going to factor what's inside the parentheses. I'm going to find two numbers that multiply to be negative 24 and add to be negative 5. And the two numbers that meet this criteria are negative 8 and positive 3. And I'm going to use that to write my temporary factors of x minus 8 and x plus 3. Now I'm going to divide both negative 8 and 3 by that value of A, which was 2. So I'm going to do that right here. And so I have negative 8 divided by 2 and 3 divided by 2. Now I can easily see that negative 8 divided by 2 will simplify to be negative 4. However, 3 over 2 is completely simplified. That means I have to take this denominator of 2 and kick it in front of the variable that's inside these parentheses. And so my final answer is negative 3 times x minus 4 times 2x plus 3. But wait, those are my factors. But why do I find factors in the first place? I find factors so that I can solve for x. I started with this original quadratic expression. I want to solve for x. And so I'm going to take my factors and set each one equal to 0. X minus 4 is equal to 0. 2x plus 3 is equal to 0. And in both cases, I'm going to solve for x. I'm going to add 4 to both sides here and end up with x is equal to 4. In this case, I have to subtract 3 from both sides first, and then divide both sides by 2. And I end up with x is equal to negative 3 over 2. That gets me to my x-intercepts, or my roots, or solutions, or zeros. Those are all names for the x-intercepts of a quadratic of 4, 0, and negative 3.5 over comma 0. Now don't forget this important step of solving, taking your factors and finally solving for x. Otherwise, all you've done is factor. You haven't really solved for x. Now pause now and write down this entire example. Let's do another example. Here we have 3x squared plus 4 plus x minus 4. All right, let me start again. 3x squared plus x minus 4. So a is 3, b is equal to 1, and c is equal to negative 4. All right, so our first step was to factor out the greatest common factor. But in this case, there is no number or expression that divides into 3x squared and x and negative 4. So there is no greatest common factor. We still have to consider it, though, just in case. So we can proceed right to step 2, which is to multiply a times c. So I'm going to multiply 3 times negative 4, and I end up with negative 12. Now I'm going to get rid of a temporarily and replace c with a times c. And I did that here, x squared plus x minus 12. Now I'm going to factor that expression the old-fashioned way by finding two numbers that multiply to be negative 12, but also add to be 1. Those two numbers happen to be negative 3 and 4, and I use those two numbers to write my temporary factors. But wait, I'm not done. I have to take these two numbers and divide both of them by the value of my A. In this case, that was 3. Now, when I do that, I divide negative 3 by 3. That's going to give me x minus 1. In the second case, though, I have 4 divided by 3. That is already in its most simplified state, and so I need to take the denominator and kick it in front of the variable inside these this set of parentheses. And I do that here, and I end up with factors x minus 1 times 3x plus 4. Now, but wait, I'm not done. Those are just my factors. I still have to solve for the x-intercepts for this quadratic, or the x's. And so I'm going to set each one of these equal to 0. Ooh, it looks like I forgot my 0 here. I have x minus 1 is equal to 0, and I add 1 to both sides, end up with x is equal to 1, and 3x plus 4 is equal to 0. In this case, I have to subtract 4 from both sides first, and then divide by 3, and I end up with negative 4 over 3. So these are my x-intercepts, or otherwise known as solutions, roots, or zeros. Pause now and write down this example. Take special note of the fact that sometimes you don't have a greatest common factor, but you can never skip the step of looking for one. Okay, one last special case. Prime quadratic expressions. Now, you know, prime numbers are numbers that are only divisible by 1 or themselves. Well, quadratic expressions are quadratics that cannot be factored. Now, in real terms, what that means is they don't have x-intercepts. If you graph them, they start and go up above the x-axis, or they start and go down below the x-axis. They do not touch or cross the x-axis at all. Here's an example. If I try to factor this, I'm looking for two numbers that multiply to equal 2, but add to be 2. Now, I'm not going to go through all the gory details on this slide. I do want you to copy them down, but the fact is there is no combination of numbers that both multiplies to be 2 and adds to be 2. Therefore, this is a prime quadratic expression. It cannot be factored, and if you graphed it, you would see that it does not have x-intercepts. Pause now and write down this example. Let's look at another prime quadratic expression. Again, we can try all kinds of combinations, but we're going to find that there is no combination of two numbers that when you multiply them equal 18, but add to be negative 7. Therefore, x squared minus 7x plus 18 is a prime quadratic expression. Pause now and write down this example. Now, I have to stop here and give you a big warning, and I want you to write this down in your notes in big letters. Prime quadratics do not have x-intercepts. They do not. If you are trying to work a problem and you can't find the factors, but you graph it and it has x-intercepts, keep trying to find the factors. You have made a mistake. If it does not have x-intercepts, it is prime. Make sure you write down any questions you have and bring them to class, and I look forward to all of your questions.